Yes. This meeting is being recorded. So you see my screen, you see my
Yes,
pointer,
yes,
right?
no problem. Yes.
Okay.
So it's already 100 people and it's growing rapidly. So when it comes to 200, I will stop.
Dima, thank you very much for organizing this beautiful meeting. It's really fantastic.
Thanks.
What I like is that the talks are relatively longer, so you can pass your message.
Right. Yeah.
Okay, I think we will start because the numbers are approaching 200 now. Good afternoon again in the second part of this session of our Moiré Magic workshop. The second speaker today will be Eli Zeldov from Weizmann, and he will be speaking about twist angle disorder and unconventional Landau levels in MA graphene. I remind you that you can ask questions by raising your hand or by writing them in question and answer chat. I will try to then let you speak lively and state the question. Don't try to mute yourself. You are muted, all of you, but if you mute yourself, then I cannot unmute you. So be careful. And Eli, the stage is yours, please.
Thank you. So I would like to thank the organizers for this wonderful school and opportunity to hear very interesting talks and to present our results. So today I'll tell you about a recent study of twist angle disorder in magic angle graphene and imaging unconventional Landau levels. So what you see here is an image of Landau levels. Each color line here is a Landau level as a function of position and the K-ray concentration. And this unique imaging technique was developed by Viram Uri and Samir Grover, and we thank our funding agencies for support. So let me start from our experimental technique, which is squid on tip. So we make very small squids by pulling a quartz tube into a sharp pipette down to a few tens of nanometers in diameter. And then we take one of our favorite superconductors and deposit on the tube in 3 steps. In the first deposition step, we coat one side of the tube, of the pipette, then the other side. And in the third deposition, we coat the apex ring. As a result, we have 2 superconducting leads connected to a ring, forming a stronger superconductivity. And in the gaps between the links, we have weak links, which form the squid at the very apex, which is ideally suited for scanning probe microscopy. So this is how it looks in SAM. So this is a lead squid. You see one superconducting lead. This is the other lead. And you can barely see the ring with the hole on the apex. We can make these devices as small as 40 nanometers. They operate in magnetic field of over a Tesla. And recently, actually, we developed a new technique of making these devices, which allow using superconducting alloys. And for example, with molybdenum, we can reach 5 Tesla operation, which is very promising for various quantum states. These devices have very low flux noise of down to 50 nanofine knot per square root hertz, which translates into very low spin noise of about 0.3 Bohr magneton per square root hertz, which means that we have enough sensitivity in order to image the magnetic field of a single electron spin. In addition, these devices are extremely sensitive thermometers, and we have recently developed thermal imaging in this work with thermal sensitivity of better than a microkelvin per square root hertz at 4 Kelvin, which allows a study of dissipation in various quantum systems. Unfortunately, I will not have time today to talk about the thermal imaging, and we will concentrate only on magnetic imaging. In addition, we attach these tips, these squids, this is the pipette you see, to a quartz tuning fork, which has a high Q resonance at about 30 kilohertz, which we use as a force sensor in order to be able to scan very close to the surface without crashing. And we can typically scan at heights of 10 to 20 nanometers above the sample surface. We use these tuning forks also to induce a small AC oscillation of the squid parallel to the surface with an amplitude of a few nanometers, which allows us to image gradients of the magnetic field in addition to measuring the magnetic field itself, which will be very useful in this particular talk. So the first part of the talk, I will focus on monolayer graphene, on imaging of equilibrium quantum Hall edge currents in monolayer graphene. This work was carried out in collaboration of Jürgen Smet and Youngwoo Kim from MPI Stuttgart and Cyprian Lewandowski from MIT. So quantum Hall state, we usually describe it in terms of Landau levels, which are full below the Fermi level and empty above the Fermi level. And the usual simple-minded quasi-classical picture is that the full Landau levels form an incompressible state with electrons orbiting in closed cyclotron orbits. The bulk is incompressible, and we have chiral edge states in which the current flows downstream in this skipping orbits picture. It flows along one direction, along one edge, and in the opposite direction in the other edge. And these are topological currents. So this is a topological state, gap topological state, and we have chiral edge modes flowing along the edges. And over the years, there were a number of experimental techniques aimed at imaging these edge states. Using either compressibility or microwave absorption or measuring potentials. However, none of them so far imaged the currents directly. So these currents were never imaged directly so far. And our goal will be to image these currents, equilibrium currents flowing in the quantum Hall state. So this is our schematic sample. It's a graphene encapsulated in HBN with a backgate of a silicon substrate. We will work at 300 millikelvin in magnetic field 1 Tesla applied perpendicular to the surface, which creates quantum Hall state, for example, like this one with 1 Landau level. And we will have 2 edge states carrying these downstream currents, the skipping orbit currents on the 2 opposite edges flowing in opposite direction. So what we have to imagine is a narrow strip of current at this edge. And this current, of course, creates magnetic field, BO-Savart. And we measure, our SQUID measures out of plane component of this magnetic field. And if you take BO-Savart of a narrow strip, this is the result at some height above the current. You have a positive magnetic field on this side, which you see here, and negative magnetic field on this side. And in principle, if you measure this magnetic field over large area, you can do inverse problem, and you can retract, you can reevaluate your current if you measure this magnetic field over large enough distance. But this inversion problem actually introduces quite a lot of noise and artifacts, and it cannot be a real-time imaging. In contrast, what we will use here is the following trick, that we use the fact that our tips reside on a tuning fork, and we can oscillate them parallel to the surface. And then in addition to measuring the magnetic field, we can actually measure its derivative, spatial derivative, dBz dx. And if you take the derivative of this Biot-Savart magnetic field, what you find is that actually it reproduces quite accurately your original current. So just simple derivative of the Biot-Savart actually reproduces the current very accurately with broadening, which is determined by the diameter of our squid and the height at which we scan. So this allows us actually, by measuring this BZ-AC, the magnetic field, the AC magnetic field at the resonant frequency of the tuning fork, to image the current directly. So for example, if we have now 3 strips of current with positive, negative, and positive current, this is the Biot-Savart, which looks quite complicated. But this is the spatial derivative, which reproduces very nicely this positive, negative, and positive current with broadening given by, as I said, the diameter and the height of our tip is essentially the intrinsic broadening of the imaging. So using this tool, we will now try to image the current directly. So for this, we have a split backgate. So we will keep the left side of the sample. So this is our graphene. We will keep the left side of the sample at charge neutrality. And we will change the carrier concentration in the right side, essentially moving the Fermi level through these Landau levels, looking for the currents flowing in the quantum Hall state. So we start at near charge neutrality. We see no currents here, except some disorder. And the first thing we'll do, we'll increase the carrier concentration to the next Landau level. And as we do that, we see a current appearing here, flowing downstream. And this is the topological current. So the signal that you see is this signal, which images directly the current. Our situation now is that we have one full Landau level, one edge state, which should give one topological downstream current. And indeed, this is what we see. So in fact, we are now celebrating 40 years of discovery of quantum Hall. So this is the first time we image the actual currents that flow in the quantum Hall edge states. And I emphasize that these are equilibrium currents. We don't apply any external current in the sample. So this is, we're in a ground state, and these are the persistent currents that flow in the system. So now we increase our carrier concentration to the next Landau level. We see that the edge state moves towards the edge. It gets denser, narrower, but surprisingly, a current flowing in the opposite direction appears here and following by another downstream current. So our situation now is here. We have 2 full Landau levels. We should have 2 edge states. Indeed, we see 2 skipping orbits. These are the topological currents that flow downstream. But very surprisingly, there is an upstream current, which we will call non-topological, that flows in between them, something that we didn't expect. If we go further, we increase the carrier concentration. These edge states move, overlap, get closer to the edge, but again, a new upstream current appears, followed by another downstream current. So now our situation is here. We have 3 Landau levels. We should have seen 3 downstream currents, which we see, but surprisingly, in between them, there are non-topological currents that flow in the opposite direction. And if we continue to increase the carrier concentration, we see another non-topological current appearing here, followed by another topological current. So what do we miss in our usual picture of description of the Landau levels and the currents? So this naive picture is in the case of non-interacting electrons. In the case of interacting electrons, The picture is a little more complicated, as described a long time ago by Shklovsky, and Weizmann, and more recently by von Klitzing and Weiss, and many other descriptions.
Eli, I have two questions now. One from
Sure.
anonymous attendee, so I cannot let him speak because I don't know who he is. What does the profile of the current indicate?
So the width of the current, so the scale here, you can see it here. So the width is about 100 nanometers, and it's mainly resolution limited by our SQUID, in which particular case was over 100 nanometers, and we scan at a height of few tens nanometers. So we're resolution limited, and when these edge states get too close, for example, these two edge states, they are too close for us to resolve, so they merge together. So actually the currents, the compressible and incompressible strips that I'll mention in a second, they're quite narrow, and we are resolution limited in our spatial resolution. So the extent is essentially describes how large is our SQUID and how close we are to the surface rather than the real width. But the position of these edge states is very accurate.
The related question is from Nicolas Leconte. I can allow him to talk. Nicolas? Can you talk?
You are muted, I see. Maybe unmute yourself.
Yeah, unmute. Sometimes it doesn't help. Anyway, the question is, how do you deduce it is upstream or downstream?
From the color, so it's a good question. The color tells us exactly in which direction the current flows, and we know in which direction we apply our magnetic field, where the Hall voltage is. So we know that these bright lines here are downstream, namely these are the skipping orbits according to the direction of the magnetic field. So these are the regular skipping orbits, and these currents and the other currents flow in the wrong direction. So the blue here is the correct direction, and the red arrows show the opposite direction of the current.
Good.
Okay, so in order to understand this, we have to look a little more careful. So if we look in the bulk of the sample, we have the usual incompressible state. Here, the Fermi level is in the gap, so the Landau levels are full. And deep inside the sample, the potential is constant, namely there are no electric fields. And therefore, in the bulk, the usual statement is the current is zero because the electric field is zero. Now, in these regions, in these blue regions, we are still incompressible. You see the Landau levels here are full in these three regions. But because of the confining potential, we have potential gradient, namely we have finite electric field. And this electric field will cause the skipping orbits, will cause the drift of the center of mass of these orbitals perpendicular to the direction of the electric field. And the current, the resulting current is simply sigma xy times the electric field. Sigma xy is quantized. So these are essentially quantized currents. These are the topological currents with bulk edge correlation. So these are the usual picture that we have in our mind of skipping orbits that carry current in the incompressible regions near the edges of the sample. But now we have also these compressible regions. And the usual thinking is that these are metallic because the carrier concentration, so the Fermi level is inside the Landau levels. So they are metallic. They screen the confining potential, namely the potential is constant in them, and therefore there is no electric field. If there is no electric field, we immediately conclude that there should be no electrical current. However, in these regions, the density of carriers changes from a full Landau level on one edge to an empty Landau level on the other edge. So the simple picture, simple-minded picture is that we have a gradient of the orbitals. And in this situation where the density is uniform, each loop cancels the current of each of these orbital cancels the current of the neighboring orbital. So we have net zero current. But now when we have a gradient, if you look, for example, on this column, the current that flows here up is larger than the current that flows here down, because here we are less dense. As a result, we have a net current flowing in the opposite direction as compared to the skipping orbits. Another way of thinking about it is that each orbital carries a magnetic moment. So this is the magnetic moment of these orbitals. And here we have a gradient. The gradient of magnetization is current. So we have here a magnetic state, essentially, which has a gradient of magnetization, which translates into current. And this current flows upstream in the opposite direction. In fact, this picture was developed many years ago by Geller and Vignale, but since these currents were never imaged, never observed before, they were long forgotten and ignored. And the main reason that these currents are usually not in our state of mind is because they don't couple to transport measurements. So in transport, you are not sensitive to the presence of these currents, but in reality, they are there and they have a very important implications. So now, if we look at
question, sorry.
Yes.
Ashley Cook, I will try to allow him to talk. Hello?
Hello?
Ashley?
Yes.
Yes, we can hear you. Please ask the question.
Hi, all right. I'm just wondering if you've explored the changes in the edge states with decreasing Fermi level and decreasing Chern number, as well as increasing, which is what you were showing here. Just because there's some recent work by Ruben Verazin from Harvard indicating asymmetry actually between these two processes, counter to what we had traditionally thought.
Okay, so we haven't seen any hysteresis, if this is what you mean. So this is completely reversible. If we go up, down, if we have edge states on both sides and so on.
It's,
so
I guess, just a difference in the localization of the edge states as you pass through the phase transition. So it might be something you can't observe here, but
which
maybe
phase
there are other
transition you are referring to?
Sorry?
What phase transition you are referring to?
Just basically when the Chern number is changing.
You are talking about twisted magic angle graphene?
No, just like imagine a Chern insulator or the quantum Hall effect, basically.
So quantum anomalous Hall, if this is what you're referring to, it usually has a hysteresis, and we understand it quite well. But usually regular quantum Hall, people don't observe hysteresis. At least we haven't seen any hysteretic behavior locally.
Okay, but you have explored this process as well, and this is what you observe.
Okay, so we haven't studied it specifically, having in mind that there might be some hysteresis, whether we should look at, but we did very extensive studies, both in monolayer and bilayer, as I will show later, and we have never encountered something that popped out and that we noticed.
Okay, thank you.
Welcome.
Thank you.
Okay, so now instead of doing this, we can just take a line cut through the edge and change the Fermi level. And what we obtain is the whole picture of these Landau levels. So this is what you see here. So this is the position. This is 0 is the edge, our artificial edge, which is this white line here. And now we reveal all these Landau levels as we naively expect. So these bright regions are the incompressible states that carry the usual topological current of the skipping orbits. And you can see how beautifully they line up due to the confining potential. But in between, these are the compressible regions. So this is the filling factor. So this is the compressible regions. And in the compressible regions, you see these black regions. This is the color scale. And you can see that these black regions are as strong, the current in them is as strong as the bright regions, which are the incompressible regions carrying the topological current. So now that we have this picture in mind, we can go and study the twisted bilayer graphene, which is the main goal of our study here. Are there any questions to this part of the talk before I proceed?
By Christian Nowakowski, I will try to allow him to talk. Christian?
Yes. Can you hear me?
Oh,
Can you hear me?
you have to
Yes, I
speak
can hear
loud.
you. Yes, go ahead.
Okay, so I was wondering, maybe I just missed it, but the imbalance of the state's population in the compressible state from left to right is just due to the presence of the confining potential. So
Correct.
right. Okay, thank you.
So this is the standard picture. We haven't changed the standard picture. The only new thinking is that the compressible regions actually carry current, and this current is of comparable magnitude as the topological current, and it flows in the opposite direction. So each edge state carries a pair of currents, one flowing downstream, which couples to the transport current, and one flowing upstream, which doesn't couple to the transport. And this pair forms the edge state rather than just one downstream current.
And another question from our room is why does the upstream current, the compressible region current, does not couple to the transport experiment?
Okay, this will take me too long to explain, but so this is magnetoelectric effect, so essentially when you apply an external current or apply an external voltage, you change the potential, and the potential drops, if you want, predominantly on the incompressible regions. So if you have additional potential applied by your source, you will increase these currents, but the integral of these currents, you will displace the position, but the integral will remain the same because the total current that flows in the incompressible region is the integral of this current density, which is proportional, which equals to the difference in carrier density. And the carrier density is fixed here and fixed here. So the integral will remain fixed, and therefore this non-topological current will be fixed between each two incompressible regions. It's a little tricky, but that's the statement.
Okay, so it's a current that flows even at zero bias.
So all these currents that we image, we don't apply any external current. These are equilibrium ground state currents. And when one applies external current, they add up to these. So the balance between these two currents will change when you apply an external potential and drive current.
Okay, great.
This is what actually happens. We don't think in these terms, usually in the quantum Hall picture, but this is the way to think about it. So without external current, they almost cancel out each other. But when you apply external current, you increase one on expense of the other, and you get a net current flowing along the edges in the edge states.
Okay, great.
Another question from Amir Ali. I allow him to talk. Amir?
Hello, am I audible?
Yes.
Okay, I think you just almost answered the question I had in mind. So because whatever you're showing is with zero bias, there's no externally applied bias. So these currents are arising spontaneously, and all you're doing is actually looking at persistent currents. So are these currents actually persistent, which will dissipate away over time because of the act of measurement itself?
No, these are ground state currents. These are equilibrium currents that are persistent, and there's nothing you can do to stop them. If you change the potential, you will move them around. But these are ground state currents. This is your ground state, and your ground state carries current. Yes.
But
and
the
they're
fact
non-dissipative. Yes.
But the fact that you're using a SQUID to actually measure the magnetic field, and that probably makes it actually there will be an opposite lens effect which will obstruct the current, right? So can that affect the current? Not at all.
No. Our measurement is passive for all practical purposes. We just image the magnetic field like you measure magnetic field of the Earth with your compass. You don't change the currents that flow. It's a very good approximation.
Okay, thank you.
And the last question for the break from Xiao Yu Wang. On the right figure, is it a specific Y cut? Sorry if I have missed it.
Yes, so this image is along this blue line as a function of backgate. So this is backgate translated into filling factor, and this is position along this blue line, and 0 corresponds to our split gate edge that we formed here artificially. Okay, I suggest we move on because it was just introduction to the main talk. So now that we have this technique at hand, we want to see what happens in magic angle graphene. And this was done in close collaboration with the MIT team, with Pablo, Johan, and Daniel. So this is our sample. This is magic angle graphene, which is encapsulated in bottom and top HBN. This is our tip. Again, we're at 300 millikelvin. We apply in 1 Tesla out of plane magnetic field. We don't drive any current in the sample. We apply a backgate. And we repeat the experiment essentially. And this is what you see. So these are the edges. The black is where the graphene is cut out. So this is the whole bar. And the red and dark blue are the incompressible strips and the compressible strips. So the red is the topological current. This is the downstream current. These are the skipping orbits. And these are the non-topological currents that flow in opposite direction. And the first striking thing is that now you see quantum Hall edge states in the bulk of the sample, whereas previously we've seen them along the edges. Here we don't see any edge states along the edges of the sample. And moreover, as we change the back gate, we see these edge states moving around, but they never reach the edges. And moreover, we expect the Landau levels and the edge states to go over the entire edges and form closed loops at equal potential contours, and we don't see any of these. The Landau levels somehow form in the bulk of the sample from nowhere and then disappear at some unpredicted points. So as we'll see later, this results from the fact that we have gradients in the twist angle in the sample. And as we will see, this gradient introduce compressible and incompressible strips in the sample. The incompressible strips carry this topological current, and the compressible regions will carry opposite non-topological current. And this is what we see here. It might sound a little complicated. So for the rest of the talk, those of you who do not prefer not to think in terms of currents, you can think of it just as a visualization of the regions that are incompressible. The red one and the dark blue one are the compressible regions. And the way we do this experiment here is slightly different. So instead of oscillating the tip and measuring, and as a result imaging the current by this trick, we do the same thing here, but we apply a small AC backgate. The edge states, they will flow perpendicular to the gradient of the twist angle. And if we apply a small AC, we will move these edge states perpendicular to their direction, namely parallel to the twist angle. And we will get the same signal, BZ AC signal, as we did before, which is proportional to the actual current. But now we're not restricted to see only one component of the current perpendicular to the oscillation, but actually it works out that we see the modulus of the current, but it gives opposite sign for the compressible and incompressible regions. So this is just, as I mentioned, you can think of it as mapping of the incompressible and compressible regions. So as we have heard a lot of talks already by now describing in much detail both theory and experimental concept of this magic angle graphene, I will skip this introductory part. But what we have to remember in our case that we have flat bands and we have the remote bands, which I will refer to as dispersive bands. And it takes 4 electrons to fill a flat band or 4 holes to empty the flat band. And these are 4 electrons per Moiré unit cell, which translates into what is called NS, the carrier density that fills the flat bands. And it's since the size of the Moiré pattern is dependent on the twist angle as a square of twist angle, this is the relation between the NS, the carrier concentration it takes to fill up the band, and the twist angle. A is the interatomic distance of carbon. And so it means that if we know NS, we know the local theta or vice versa. So this is what we will use for mapping the twist angle. So now I flip this, this band structure. And let's first look at the conventional usual transport measurements. So this is ρxx, Rxx measured in the sample as a function of magnetic field and carrier concentration. So this is 4 electrons that fill the flat band. So this is the single particle gap plus NS. This is minus NS, minus 4. So all this part is the flat bands, and these are the dispersive bands. And what we observe is the usual transport picture. We have insulating state at the single particle gap, and we see these correlated states with insulating behavior at integer fillings. In addition, at high magnetic fields, we see Landau levels emerging from charge neutrality and some Landau levels emerging from partial filling from these correlated states. And you can barely see Landau levels in the dispersive bands. So if we take a line cut through this data at 1 Tesla, this is what we see. So this is Rxx at 1 Tesla as a function of carrier concentration. So you see the 2 NS insulating states. You see the strongly correlated insulating behavior. You see some Shubnikov-de-Haas oscillations at 1 Tesla, which eventually will turn into fully Landau levels. And you hardly see any oscillations at any other filling factor. So now we can repeat this measurement locally. So this is this BZAC signal that I mentioned before that is proportional to the current at some point in the sample. And each of these peaks means that now an incompressible strip has passed under our tip. So if we are at the peak, there is an incompressible strip under the tip. And if we're at minimum, there is a compressible region. And you see it actually gets negative. This is the current flowing in the opposite direction. So it's actually looking at the Landau levels locally. And what the first thing that you clearly see is that locally the Landau levels are fully developed. We see very sharp incompressible strips and broader compressible regions, whereas globally you don't see essentially almost anything of this except in this region. And this is because of the global disorder, as we will discuss later. So the height of these peaks tells you how much current flows in the incompressible strip, which is proportional to the gap, Landau level gap energy. And the distance between the peaks tells you how much carriers you need to fill a Landau level, namely the degeneracy of this Landau level. So we see that at charge neutrality, the Landau level is 8-fold degenerate, and the nearby Landau levels are 4-fold degenerate. The Landau levels in the dispersive bands are 4-fold degenerate, but occasionally we find an 8-fold degeneracy. At half filling, at filling factor 2, we see 2-fold degeneracy, and at 3/4, we see 1-fold degeneracy. So the first thing that we will do with this data is to extract the local twist angle by the following argument. So let's zoom at the dispersive bands. So these are the Landau levels that we see in the dispersive bands. They are 4-fold degenerate. So we know exactly that we need to put 4 electrons per phi naught with the applied field. And the distance between the opposite Landau levels in the 2 dispersive bands is this degeneracy plus 2ns. So first we have to fill up by ns the flat band, and then we have to add 4 electrons per each Landau level until we reach this point. So for example, the distance between these 2 Landau levels is 2ns plus 24 b apply over phi naught. So from this distance in the baguette, in units of baguette, we can immediately extract ns. And if we know ns, we know the local twist angle, the local theta. These peaks are extremely sharp. They're essentially 1 point sharp in our data. And we acquire data here with steps of 2 millivolts. So we can determine the position of this peak within 2 millivolts, whereas the distance between these two peaks from here to here is about 20 volts. So we can determine the position with a precision of 10 to the minus 4, which translates into really remarkable accuracy in measurement of local theta, which translates into 0.2 millidegree of twist angle. And this is with a spatial resolution of about 50 nanometers, as we will see later.
There was a question. There was a question from Chanli Huang about spatial resolution, which you have just answered, I understand.
Exactly. So our squids are typically 100 nanometers for various reasons, but we can actually show that the precision to which we can determine the position of these Landau levels, because they are extremely narrow, as we will see later, with spatial resolution of about 50 nanometers, which is about 4 Moiré unit cells. So we can tell that these 4 Moiré unit cells have a twist angle with this precision, and the nearby have 0.1 millidegree or 0.2 millidegree different twist angle. I will show you later 2D maps, which take longer to acquire, so we take them with more crude scanning points, which translates into accuracy, a relative accuracy of 0.1 of 1 millidegree. So this was the measurement at some specific point in the sample, but now we can repeat the same thing along a line through the sample, and this is how it looks. So these are the Landau levels as a function of position and the backgate voltage. If the sample would be ideal with no disorder, these lines should be straight vertical lines. So the Landau levels should be position independent in the sample, but we see that they are strongly position dependent. So now, using the same trick of measuring the distance between the various Landau levels, we can extract the local NS as a function of position. So this are the 2 dispersive bands. This is the flat band, and this is the NS, the density at which we fill the flat bands. And the distance between these two NS, as we saw before, is proportional to twist angle square, actually. So first we can map out NS as a function of position. So this is this distance. So this is NS as a function of position over these 3 microns. And it changes by about 10%. And NS, from NS, square root of NS is essentially the twist angle. So this is the twist angle variation along this path. And the NS changes by 10%. It means the twist angle changes by 5% from about 1.12 to 1.17 over this particular path. So NS determines how much, twist angle determines your NS, namely how much carriers you have to put in order to fill this flat band. So namely the distance between these 2 curves, which is twice NS. So the difference between these 2 curves gives you the twist angle disorder, but the addition of these 2 lines will give you charge disorder, because if you have charge disorder, it shifts your your charge neutrality point, and it will shift these 2 lines in the same direction. Twist disorder moves these 2 lines in opposite direction. So now if we take the sum of these 2 lines, we can also extract the local charge disorder, which is few times 10 to the 10, comparable to charge disorder in state-of-the-art monolayer devices. And what you see immediately here, the twist angle disorder gives variation in NS of few times 10 to the 11, which is at least an order of magnitude larger than the charge disorder. So we are dominated by twist disorder. And this you can see by your eye that these 2 NS lines are essentially anti-symmetric, whereas charge disorder would shift them symmetrically. The next observation here is that now that we know the position of NS, we can also know the position, the local position of these fractional fillings. So the first striking observation here is that the Landau levels in the dispersive bands are very robust, in contrast to global measurements where you hardly see Landau levels in the dispersive bands. And this is because we are dominated by twist angle disorder, which smears the global Landau levels. And the Landau levels near charge neutrality are also quite robust. And you see that they are much straighter than those. And these Landau levels are mainly sensitive to charge disorder and not so much to twist disorder. So therefore, they survive better in global measurements. So in global measurements, these ones are the main thing that you see. Whereas the Landau levels in the correlated states are extremely fragile. You see them only at very few positions, here marked in these regions. They're extremely sensitive to position, and which we conclude that the fragile states are the correlated states are very fragile with respect to twist angle disorder. We will come back to this point later. So far we have seen what happens at one point, what happens as a function along a given line. But now we can do the full 2D imaging. So now I'll show you a movie of what happens in this rectangle, in this square region. You see Landau levels forming very complicated structure, and they evolve through the sample. We can take this movie and construct a 3D tomographic imaging of the Landau levels. So this the two spatial directions, X and Y, and this is the backgate. And we get a tomographic 3D representation of the Landau levels. So Landau levels form manifolds, two-dimensional manifolds in this three-dimensional space. And the red ones are the incompressible regions. The dark are compressible regions. So these are inside the Landau levels. So for example, these three Landau levels are fourfold degenerate. This is eightfold degenerate. And these are again fourfold degenerate. And by tracing, and there are regions that show no Landau levels at all. And by tracing these Landau levels, we can, by the same trick, we can extract the local twist angle. And this is the twist angle map that we derive. So it shows a quite complicated landscape with a variation of about 10% from 105 to 118 degrees. And in addition to this complicated landscape, the striking thing here is that there are quite significant regions that show no Landau level, no magic angle physics at all. These are the regions that show no Landau levels. And if we compare it to AFM image, and we find the bubbles, so bubbles are here shown in black contours, apparently kill completely the magic angle physics within the bubbles, as well as within about half a micron surrounding them. And in addition, we see quite significant areas that show no magic angle physics without any clear observations in AFM. So our conclusion is that these regions are either strongly disordered or they have twist angle which is significantly below or above the magic angle.
There are two questions which are somewhat related to this figure. One is, what Adrien Rousseau, what do you mean by twist angle disorder? I think this figure explains it perfectly.
I'll come back to this. It's a good question. This will be the rest of the talk. Will focus on this. Yes.
Yes, and the second one is why, from anonymous attendee, so I cannot give it. Why Landau level near the charge neutrality is insensitive to twist disorder? Isn't it counterintuitive?
Okay, so this will take me too long to explain. So I will skip this question, and we'll come back to it at the end if we will have extra time. But
Good.
Okay, I have to go back and to explain it in more detail. Because essentially at charge neutrality, when your Landau level is at charge neutrality, you don't care what's the twist angle. I'll come back to this in the last slide. Okay, so now, as we said, the Landau levels have to follow the bottom of the dispersive bands, namely have to follow the NS. So this map of twist angle is essentially potential map that the Landau levels feel. So for Landau levels, this map, or square if you want, of this map is essentially the potential. So the Landau levels, as we increase the backgate, they should form at the minimum of this potential landscape, and they should climb this landscape, if we look, for example, at this point, following equipotential lines, which are actually equitheta lines. So if we look at this movie again, we see Landau levels forming here at the minimum. They climb this potential, forming these arcs, as the landscape shows us. And what is remarkable is that they just start here and end here, don't close the full loop as we would expect. They just dissolve, disappear in these regions, which are, as I said, either disordered or have very different twist angle. This is another very interesting region. So here we have two minima. We have a minimum here and a minimum here, and a saddle point in between. So the Landau levels should climb from one side, the other side, that should merge here, and they split and move along these two orthogonal potential gradients. So you can see it in the movie. So you see Landau levels forming here and forming on this side. They come, they merge, split, and move in opposite direction. Here another pair comes, merge, split, and move into opposite directions. So now that we understand this landscape, we can understand the dynamics, the complicated dynamics of these Landau levels. We can also do some statistics of the twist angle disorder. So, this is the histogram of this disorder. So you see that the twist angle here varies by about 10% in this sample. It has quite a broad and rather uniform distribution. Here's another sample in the form of a whole bar. And when we map the magic angle here, we see that the twist angle is quite uniform in the center and is lower at the edges. And the histogram of this sample shows two peaks, but comparable overall width. And now we can compare to the twist angle that one derives from global transport measurements. And we see that in this sample, the global measurements give us a twist angle of about 1.15, which coincides quite close to the maximum of this distribution. But if we look at this sample, we see that globally we derive an angle which is 106, which is at the edge of this distribution and overlaps this maximum. And it's quite clear why, looking at the map. This is a whole bar. We drive current from here to here and measure voltage from here to here. So in transport measurements, we're mainly probing the center of this whole bar, which has a higher twist angle, which is this distribution here, and it's more uniform. And this is the reason, while transport doesn't probe these regions, which have a smaller twist angle. Since we have also very high resolution imaging of this twist angle, we can also look at the gradients of twist angle just by taking a numerical derivative. So this is the absolute value of the twist angle gradient, which is on the order of up to 0.1 degree per micron. And what you see, surprisingly, is that instead of having smooth variation in twist angle, actually you see a mosaic of regions in which the twist angle changes smoothly, but then there's a network of quite sharp jumps. And if you look at this sample, you see very similar structure. So essentially the conclusion is that it's more like a grainy structure with some smooth variation in twist angle inside these domains, and a network of stacking folds across which the twist angle changes more abruptly due to this presence of stacking folds, which relax the strain, as has been seen by STM and TEM measurements. We can also extract the charge disorder, as I mentioned previously, and this is the map of the charge disorder in this sample with distribution a few times 10 to the 10 per centimeter. So now, having derived this map, we can look again at the transport and understand the percolation physics. So these are the transport measurements, global transport measurements of these two samples, which are quite different. So if we look at this sample, we see a fully developed superconducting state with zero resistance and finite critical current. And looking at the twist angle map, we can understand that superconductivity can percolate between these voltage contacts because we're close to magic angle in the central part of the sample. This sample, however, showed suppression of resistance down to a couple of hundred ohms, but it never reached the zero resistance state and never shows critical current. And again, looking at this twist angle map, it becomes evident why this is the situation, because there is no percolation path between the voltage contacts of the entire magic angle. We have significant regions which are not magic angle. Also, by the same token, we see that this sample shows much more pronounced Landau fans, both near charge neutrality and even in the dispersive bands, and in particular in the correlated states. And this is again because the twist angle is more uniform in the central part of the sample, and it's continuous. In this sample, one can hardly see any resemblance of Landau fans in the dispersive bands and in these fractional fillings in the correlated states, because there is no percolation of magic angle regions, and because there is higher disorder, twist angle disorder in these samples. So it emphasizes the fact that these the correlated states are very sensitive and fragile with respect to twist angle disorder. So now
Anonymous attendee, how much can the twist angle disorder affect the different emergent phases in the MATBG?
Good, so this is exactly the purpose of this last slide. And if I don't answer the question here, please ask me again. So now we come to the why twist angle is important, twist angle disorder is important, and what are the implications. So what I want to emphasize is that actually twist angle disorder is a new type of disorder, very different from usual types of disorder that we used to think of. The first point is that it's band structure disorder. Namely, at each point in the sample, the band structure is different because the band structure is very sensitive to twist angle near the magic angle. The second is that it's effective mass disorder. So actually the carriers have a different effective mass in different places in the sample, and they change their effective mass as they flow through the sample. And this next point is that gradients of twist angle break the local symmetry. So now we have a situation where the local symmetry is broken, but it's broken differently at each point. And moreover, the gradients have direction. So the breaking of the symmetry becomes both position dependent and orientation dependent throughout the sample. But there are several additional important consequences that I will describe in more detail now. So let's consider we have two regions with slightly different twist angle. This region has a larger twist angle than the left one. So this is the schematic band structure. So we have flat bands, and this is the dispersive bands. And since the twist angle is slightly larger here, we will have a slightly higher NS here and slightly larger density of states in the flat band regions in this side than in this side. So let's start with a situation that we're at zero backgate. So at zero backgate, the Landau level is at charge neutrality in both of these regions. All the states below the Landau level, below the Fermi level, sorry, are full. The levels above the Landau level are empty, and there is no significant difference between these regions. So this comes back to one of the previous questions, why near charge neutrality, near charge neutrality, we're not so much sensitive to twist angle disorder, because it affects basically the density of states quite far from the charge neutrality point. But this situation changes drastically as we apply backgate. So let's assume we apply some backgate, which will result in carrier concentration in the left side of the sample, which will give rise to some chemical potential, corresponding chemical potential here. And the density of carriers that we induce in the sample will be given by the backgate and the capacitance. but the backgate is the same in both regions. The capacitance is the same. So it means that in this side of the sample, we should induce roughly the same carrier density. But since the density of states here is larger, this will translate into a smaller chemical potential. But the Fermi level has to be fixed. It is 0 throughout the sample. Variations in chemical potential means that there must be corresponding variation in electrostatic potential. So if there are changes in chemical potential, they will be compensated by changes in electrostatic potential. Changes gradients of electrostatic potential is in-plane electric field. So now in this situation, we will have in-plane electric field, which is proportional to the gradient of electrostatic potential, which equals to the gradient of chemical potential, which results in very strange situation. We are used to think that a metallic state has to screen electric fields, and therefore we should have a constant electric potential within the sample in a metallic state. Here we have a metallic state which doesn't screen the electric field. On the contrary, it generates electric field. So we have large electric fields in the sample, in-plane electric fields in the sample in a metallic state which cannot be screened. So we have large unscreened electric fields in the sample, very counterintuitive. And moreover, these electric fields are gate tunable. So if we are at charge neutrality at 0 backgate, we have no electric fields, and these electric fields grow with backgate. So this is a numerical calculation based on actual band structure calculation. And let's assume our twist angle changes from 1.1 to 1.15 degrees over 2 microns, comparable to what we see in experiment. So the calculation shows us that the potential, electrostatic potential, changes linearly, since the twist angle changes linearly here, and which causes internal electric field in this twist angle gradient region, which is very significant. It's here it's about 0.5 kilovolt per meter. The corresponding carrier concentration is very mild. So the change in carrier concentration is just 10 to the 8 compared to 10 to the 12, our density of carriers here. So essentially the carrier density is fixed by the backgate. But despite the fact that the carrier density is constant, we have very large internal electric fields which cannot be screened by definition. This situation becomes even more dramatic when we apply magnetic field. So now it's the same situation, same calculation, but with 1 Tesla, 1.2 Tesla magnetic field. In this situation, the Landau levels in the dispersive band, for example, will be position dependent, and which means that we will form compressible and incompressible strips across the sample, and the chemical potential will jump sharply across the incompressible strips. And our calculation shows that the width of these incompressible strips is very narrow. In this particular case, just 40 nanometers. If there is a jump in chemical potential, there must be an opposite jump in electrostatic potential. So now we have edge states inside the bulk of the sample, which explains how come we see these edge states and Landau levels in the bulk of the sample. And moreover, this will give very narrow incompressible strips with huge electric fields with them. So in this case, we have an electric field which reaches 100 kilovolt per meter, which creates very intense, very narrow currents, topological currents flowing in these incompressible regions. And these peaks are exactly what we see. So the peaks that you saw in one of the first images, every time such an incompressible strip passes under our SQUID, we have this peak in signal, which is proportional to this current. And again, the charge is quite uniform. This is a variation of the order of 10 to the 9 throughout the sample. Moreover, this calculation shows us that there is an accidental crossing of Landau levels here. So since in the dispersive bands, there are actually 2 bands that are almost degenerate, not exactly degenerate, the Landau levels occasionally may cross. So these Landau levels are 4-fold degenerate, And at this point, this Landau level, which consists of actually of 2 Landau levels from 2 different bands, will be 8-fold degenerate, as we see in experiment.
I have
So
several questions.
Yes, so this is my last punchline, and then we can turn to questions.
Right.
So, so the take-home message here is the twist angle disorder is fundamentally different from other types of disorder that we know. It changes the band structure, the effective mass, and the local symmetry inside the sample, and it creates huge unscreened electric fields in a metallic state in the sample, which dramatically changes the entire physics of the Landau levels in the quantum Hall state. So let me just thank the people who did all this work. So all the imaging was carried out by Aviram Uri and Samir Grover at Weizmann. The SQUIDs were developed by Kusik Bagani with the help of Yuri Masiedov. Nadav Aurha carried out numerical calculations. Elal Lachman built the scanning probe microscope in the helium-3 cryostat. The twisted bilayer graphene, as we discussed, came with close collaboration with the MIT team. The band structure calculations were carried out by Mikita Koshino, Pyung-Wook Moon, and Alex Cross. The monolayer graphene from MPI Stuttgart, Jürgen Smet and Young-Wook Kim. The HBN from NIMS, as usual, and the superconducting electronics, the SQUID array amplifiers, came from Martin Huber from UC Davis. So let me just leave you with these movies, and I'll be happy to answer your questions.
Thank you very much, Ali. It was fascinating, really beautiful. There are several questions concerning the nature of this twist angle disorder. Christian Nowakowski. Christian, you have to unmute yourself so I can let you speak.
Can you hear me?
Yes. Now, yes.
Hello, I have a question regarding the twist angle disorder in one of your slides where you showed 2 devices. And the second device, which is device B, it has, it seems like that you were not able to map the twist angle properly at the edge of the edge of this sample. And my question is it related to the resolution of your technique, or maybe it deals with the device fabrication, namely the RAE etching that introduces disorder?
Okay, so we image the entire, so all the region that is shown here has been imaged. And in these gray blue regions, there was simply, we do not resolve any Landau levels. You can see it clearly here. So there are Landau levels in this part. There are no Landau levels, for example, at these spots here, which are the bubbles. And there are no Landau levels in all these regions here, for example, and no Landau levels here. Similarly here, you see no Landau levels here, no Landau levels here. So these grayish regions, we image them, but there are no Landau levels there, either due to disorder or due to very different twist angle. Does it answer your question?
Yes. And just one more follow-up question for the first device where you explained the quantum Hall edge imaging. So those devices essentially fabricated in the same way, right? And there you didn't have problems seeing this skipping orbits. Is that correct?
You are talking about monolayer graphene.
Exactly, yes.
Yes, so we don't see any, so in monolayer graphene, we see charge disorder. So for example, you see here a region, or actually in a movie before that. So what happens in a regular situation is that, so let me go to this. I didn't have time to describe it. For example, you see currents here. This is not noise, this is not artifact, these are actual currents due to impurities. So you have charge disorder here in the center, which causes circulating currents to flow around it. And since in this technique with tuning fork, we measure only Y component of the current, you have to imagine a current going down here and up here, circulating around this charge disorder. So these point charge disorder will create a monopole magnetic response, which unfortunately I didn't have time to describe it. You can see another one here and so on. So charge disorder creates circulating currents, equilibrium, ground state currents circulating around it. But other than that, you see edge states along the edges of the sample. You don't see Landau levels in the bulk. Of course, due to charge disorder, you will see at the transitions, but this is very different physics. So we understand very well the physics of charge disorder. In magic angle graphene, we see both charge disorder, but this is minor effect. The major effect is magic angle, the twist angle disorder, which introduces much stronger and very different type of disorder.
Thank you.
So for example, in this state, when you are in the compressible, in metallic regions, these currents are screened. These electrical potential are screened, and these currents, these topological currents are absent. Whereas in magic angle graphene, you cannot screen the electrostatic potential, and you will have incompressible and incompressible states everywhere.
Thank you.
Okay, I have a question from Maximilian Kögl. I allow him to talk. Maximilian.
Yeah, hello. Thank you for the talk. So I have a question. Can you switch to the slide where you show the gradients of the twist angle disorder?
This
so,
one? Following one?
I think it's the following. So basically the image showed that, this one, that there are, it looks like wrinkles somehow, like the twist angle disorder gradient is, are very sharp lines, which you said probably originate from strain inside those structures. So I was wondering, these strains look quite locally, so shouldn't they be attributed to something that can be observed in the AFM?
Okay, so the first part of your question, so if you imagine that you have to rotate your one layer of graphene relative to the other with an angle which varies in space, obviously you will introduce a lot of strain. So instead of uniform rotation of two sheets, you have to deform them, which will introduce quite a lot of strain, and this strain has to relax somewhere. So there were some beautiful experiments by STM, by Evan Ray, and by TEM in Harvard group, showing that showing these stacking folds and very similar network of abrupt changes in the local twist angle. They were performed, the TM was performed on samples with much smaller twist angle. They couldn't do it at magic angle graphene, but I think the physics is the same. So our interpretation is that the strain has to be relieved, and it occurs through this network of stacking folds.
There are many questions waiting, so
thank you.
I'll try to be brief. Everybody. Two questions from anonymous attendee. What is the tolerance of superconducting state to the twist angle disorder? Has there been a progress or how to simulate twist angle disorder in real or reciprocal space models, like binding approaches, continuum models?
Yes, so we would love to image the superconductivity. We have some ideas how to do it, so I hope we'll be able to do it in the future. Yes, so looking at these maps, you can imagine if superconductivity is strongly linked to the local twist angle, for example, superconductivity occurs only at, let's say, exactly 1.1 degree. So you can imagine that superconductivity should exist only along this contour, and let's say this contour. Or if you allow yourself to think that superconductivity exists over a range of some angles, let's say this, so you will have patches of superconductivity here and here, and not let's say at these angles. So obviously, the regions where superconductivity will exist will crucially depend on the local twist angle, but we don't know how to correlate the map of twist angle to a map of superconductivity, at least yet. And from a theoretical point of view, I'm not sure whether there's such detailed information is available now. And of course, the band structure also changes. If you have a gradient of twist angle, you break symmetry, and therefore this can also affect strongly superconductivity. So it's not only the angle itself, but the gradients of the angle might be even more important than the variation in the angle itself.
The last one from Anonymous, does the magic angle imply strain?
So if you take two sheets and rotate them rigidly, then you will have a uniform twist angle, and to a good approximation, there should be no strain. But if you want to rotate with one angle at one point and with a different angle at a different point, obviously you will introduce strain.
I have another question from Chun-Li Huang. I allow to talk, Chun-Li.
Thank you. So simple question, can you decrease the density of stripes in your samples, say by putting on a boron nitride? Does that help? Thank you.
So all these samples are state-of-the-art samples encapsulated in boron nitride. So all the imaging is done through the top boron nitride. Our samples are encapsulated. As I said, the twist angle, these samples come from MIT. They're regular transport samples, so we can simultaneously measure transport and image local Landau levels and the local twist angle. So these are as good samples as currently are available, at least to the best of our knowledge.
Yeah, so I'm asking if you can decrease the density of stripes. Do you know how we can do that?
Stripes, you mean the incompressible and compressible regions?
That's right.
So the distance between them will scale with magnetic field. So if you go to lower magnetic fields, the degeneracy will be smaller, and therefore these stripes will be narrower and narrower. If you go to larger and larger magnetic fields, these will be, you will have less and less stripes, these stripes. And eventually, if you go to very high magnetic field, hopefully your entire sample will become a single Landau level, and then you will, in principle, should see zero RXX in magic angle graphene. And indeed, if you go to high enough fields, so that the degeneracy of the Landau levels becomes larger than the variation in twist angle in terms of NS, you should get full quantum Hall quantization, as people have seen at very high magnetic fields in twisted bilayer graphene indeed.
Okay, thank you.
Time is running very fast. There is a question from Oscar Dafek. I allow to talk. Oscar. Oscar? Okay, I read it then. Is it possible to observe vortices in the superconducting state of the twisted bilayer using this technique?
In principle, yes. In practice, it will probably be very difficult. So first, you will have to have a very uniform superconductivity, because if the superconductivity is highly non-uniform, as we would imagine from these pictures, you will have a lot of variations in the local magnetic field that might look as vortices, and it will be very hard to tell which of them are real vortices. But more severe problem is that your penetration depth, magnetic penetration depth, lambda, in the limit of 2D diverges. So your vortices, in terms of their magnetic imprint, they diverge. So the vortices, their magnetic size becomes comparable to the size of the sample, and therefore you have to do it at very low fields. And so I presume it will be very hard to see them. But again, this is something we would like to try at some point.
Okay, the last question by Hyunjin Kim. Hyunjin, I allow you to talk.
Can you hear me?
Yes.
Yes.
So thank you so much for the talk. I would like to ask have you ever observed 4-4 degenerate Landau level in charge neutrality of flat band instead of 8-fold degeneracy, because there was recent theory paper suggests that if symmetric breaking can be an origin of 4-fold degeneracy in the flat bands of the Landau level, and at certain magnetic field and maybe a certain strain, even the Landau level could be like 4-fold degenerate instead of 8-fold.
Thank you for the question. So far you can see it here. So as I said, the distance between the Landau levels tells you directly the degeneracy, and we know, so these are 4-fold degenerate, and you can see that the 0th Landau level is 8-fold degenerate. But of course, when you go to regions which are more disordered, as you can see, for example, here, things become more complicated. But as a rule, wherever we see clear Landau levels, we see at our fields, which so far are limited to about 1 Tesla, 1.5 Tesla, we see clearly 8-fold degeneracy at charge neutrality and then 4-fold degeneracy away from it. But sometimes you see the broken states, and you can see here, but even here, you see more complicated structures.
Okay,
thank you so much.
Close this session because in 10 minutes we have a hot topics already starting. I would like to thank Eli in the name of all of us for fantastic talk, and all the participants, and see you soon in the next talks.
Thank you very much.